Hello everybody. So we are solving some more examples here, and for the example that we are going to see here is the example of the two extractors. And for this example we have two extractors, one mixer and the distillation column, and we had a column for each one of them, and then we have the overall and the process. So for extractor 1 we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 variables. The number of given variables is 1, 2, 3. Given variable 4. We have 4 given variables. The number of equations is AWM. So we have three equations, and the number of additional relation is 0. So this is 9 minus 7 is 2. For extractor 2 we have 3, 3, 3. So it's 9 plus 1, it's 10 variables. The given variables are 1, 2, 3, 4, 5, 6 given variables, and the number of equations is 3, and the additional relations is 0. For the mixer we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 variables. The number of given variables is 1, 2, 3 given variables, 3 equations, and no additional relations. So this is 3 degrees of freedom. For the distillation column, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9 variables. We have 2 given variables here, 3 equations, and no additional relations. So this makes the degrees of freedom is 4. And for the overall it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have 13 variables. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 13 minus 9 given variables. We have 3 equations and no additional relation. So this makes the degrees of freedom 1. And finally, for the process, this will take some time. So number of variables, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 variables. The number of given variables is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 given variables. The number of equations is again the summation of these 4 units, or number of equations in the 4 units. So this is 12, and the number of additional relations is 0. So degrees of freedom is 1. So again, from here we can know that we need to assume something, and we knew when we did the solution that the distillation column is where we need to assume an information in stream 9 or stream 10, because this is something that we can find from here. Again, this is one of the good things about the degrees of freedom table, is that if you think of the information that you can get or give to the distillation column, it's either going to be through the solution of the distillation column after solving the mixer. So you can get 3 information going to the distillation column, which is not going to be enough, or from the overall loop, and still the overall loop cannot be solved by any means, because the overall loop can all the missing information in the or the other information in the overall loop are already known. We know stream 1, 2, 5, and 6. So we have no missing information except these 2 streams. So even if I solve the rest of the units, the overall loop is not providing any new information. The overall is still not going to help. So so from this we know that the process is where we can that we need one information, and from the degrees of freedom here we can know that we can assume this information in the distillation column. And this is what we saw, that we were able to solve the 2 extractors, and from the 2 extractors we solved the mixer, and from the mixer we were stuck because we don't have enough information to solve the distillation column. Anyway, so this is one extra case that we saw that we need to assume an information, and this was even before we start the solution. Okay, so this was even before we start the solution. And when we started the solution, we started with the two extractors, and from the two extractors we solved the mixer, and from the mixer we moved forward. But before this we were not aware that we were going to be stuck at some point. But now we know that we need to assume something. Now let's look at this example here. We have three reactions in a reactor, and we have two information or additional relation, the fractional conversion and the relation between R and N in stream number 1. And this is the single pass conversion, if I'm not mistaken. So for the table, for the mixer, we have 1, 2, 3, 4, 5, 6 variables. We have number of given variables is 1. Number of equations is 2, and we have one additional relation, which is second one, which makes the degrees of freedom equal 2. The reactor, we have 1, 2, 3, 4, 5, 6, 7 plus 3, so it's 10. The number of given variables is 1, 2, 3 given variables. The number of equations is 5 components, so it's 5 equations. The number of additional relations is 1, which is the fractional conversion, so degrees of freedom is 1 for the reactor. Solving the separator, the number of variables that we have is 5 plus 2 plus 3, so it's 10. The number of given variables is only 2. The number of equations is 5. The number of additional relations is 0, so it is 3. The splitter, we have 1, 2, 3, 4, 5, 6 variables. We have 0 given variables. We have 2 equations. We have 0 additional relations. We have the splitter restriction. I forgot it. So it's 2 minus 1 times 2 minus 1. So we have 3 degrees of freedom. For the overall, we have 1, 2, 3, 4, 5, 6, 7 plus 3, because we have 3 reactions. The number of given variables is 0. The number of equations is 5. The number of additional relations is 1, which is number 2. And for the degrees of freedom is 4. And again, you would expect that we need to assume something because we don't have any flow rate. So for the process, the number of variables is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 plus 3, so it's 21. 3, of course, the 3 extensive reactions. The number of given variables is 1, 2, 3 given variables. The number of equations is the summation of these numbers, so it's 14. The number of additional relations is 2 plus the extent of reaction, so it's 3. I mean the splitter restriction. So by counting this, you will find that the degrees of freedom is 1. So again, you would say that we need to assume some information, and this information would be in the reactor. So I can assume stream 2, for example, or stream 3 flow rate. And this is something that I have no problem with, but let's assume that you have already a given flow rate. Let's assume that you have already a given flow rate. I think this is a case that we will discuss later. If you have a given flow rate, and this flow rate, let's say, is the flow rate of stream number 7. Okay, so if it's stream number 7, you are adding one information to the overall and one information to the splitter. So splitter is not solvable, the overall is not solvable, but then you know that you cannot solve because this would be 0. And in this case, you have to find the solution with the given information. So this is one thing, and this is, by the way, this is one thing that I did before, and I didn't tell you why I did this, which is the last problem before combustion, which is the relocation of bases. The way you can tell that you can relocate the bases is by looking at the process column, because if you have the flow rate in stream 7, then the process is 0 and no unit is 0, and this is where you can tell that you can solve it, but you have to find a way. Because assuming an information will contradict with one of the given information that you have here. So this is why the process is very important. The process column is very important. It's extremely important for this reason. Because you can start the solution by assuming an information and going with the solution. At some point you'll find that the solution is not working. Some equation doesn't have the right hand side and left hand side are not equal. So this is what you can use to do this. Okay, I'll take this example, and this is going to be the last example for now, and we will continue next time. So this is the reactive system with inerts, and this is the problem for ethyl benzene and production from ethylene and benzene. And we have the feed, as you see, then the reactor, then a separator, and we have this reaction here, and we have 5 relations, one which is the conversion in the reactor, and the rest is just the separation recoveries in the separator. So for the reactor we have 1, 2, 3, 4, 5, 6, 7 plus 1, so it's 8. The number of given variables is 3. The number of equations is 4. The number of additional relations is 1, so it's solvable. The degrees of freedom is 0. For the separator, it's 4 plus 4 plus 4, it's 12. We have the number of equations is 4. The number of we have no given variables, 4 equations and 4 additional relations, so its degrees of freedom is 0. For the overall, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 variables. 4 plus 4 plus 3 is 11, plus the extent of reaction, so it's 12. The number of given variables is 3. The number of equations is 4. I'm going quickly because we already did this before, so I don't want to be wasting a lot of time. The number of additional relations is 0. We don't have any, so the degrees of freedom is 5. For the process, the number of variables is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, plus the extent of reaction, so it's 16. We have 3 given variables. The number of equations is 4 plus 4, so it's 8. The number of additional relations is 5. We have these 5 relations, and so the degrees of freedom is 0. So we don't need to assume anything. This was the first scheme for this process, and then we did more modifications to the process to recycle the stream. And this is going to be a very, very, very important case, because in this case you'd see how the degrees of freedom table is going to make a lot of sense here, and I'll keep it for next time. So I'll see you then.